Today we're going to be looking at something different. We're going to be looking at some physics, and this topic we'll be looking at kinematics. And in this question, we're going to be looking at a ball of mass m with speed v that's incident on a larger mass that has a spring attached to it and essentially bounces off, and we're asked to figure out the maximum compression of the spring. Now, how we're going to do that is through a series of deductions that involve using Newton's third law. But before we do that, it might be tempting to just approach a problem simply in the lab frame by looking at the energy before and after. So in this case, it'll be half little m v squared equals, and we're a bit confused here, and we're going to have to figure out why we're confused, because first, we have little m. This is going to be after the collision, after they interact with that has a big mass attached to this, and they're both going to have speed. Speed here. They're both going to have some sort of speed alongside energy being stored in the spring. So there's too many things going on, and it's going to be hard working in this reference frame. So what we're going to have to do is change our reference frame, and the motivation for that is by considering the center of mass, and we'll see why. First, let's have a look at the center of mass. XCOM equals the sum of the moments of the individual masses divided by the sum of the mass, the total mass of the system. Then all we have to do is if I multiply the total mass of the system on both sides, I'll get sigma mi xcom equals sigma mi xi. If I differentiate both sides with respect to time, I'll get sigma mi, I should put this in brackets, velocity of the center of mass equals the sum of the momentum, the total momentum of the system. I'll get this expression, and then if I differentiate with respect to time one more time, I will get sigma mi acom, which is the acceleration of the center of mass, equals sigma fi. Now, if all the forces are internal, that means they're all subject to Newton's third law. So the sum of the forces must always be zero if all the forces are internal. And you can sort of justify this to yourself. If I do one mass here and another mass here, and I've labeled them object 1 and object 2, the force on object 1 by 2 is going to be F21, the force on object 2 by 1 is going to be F12, and they're going to be equal and opposite. It doesn't really matter what labels you have them, as long as you make them equal and opposite. Therefore, the sum of the forces are all going to be 0. That means if we integrate up, now if we go up, that means the sum of the momentum needs to be constant, which is something you already know. But more importantly, the velocity of center mass is going to be constant. So if we just move our reference frame with the same speed as the velocity of center of mass, the speed of the center of mass, we will have the center of mass stationary. And in this stationary center of mass frame, all we have to do is just focus on the center of mass, watch the masses come together, and then come together to their maximum compression, and we can then work out from there. So how do we work out the velocity of the center of mass? Well, we have a formula right here. It'll be the sum of the momentum. Well, in this case, that's pretty easy. I have my little mass moving with speed v, and big mass, well, that's going to be stationary. So the sum of the momentum is actually just going to be mv. And if I then divide that by the total mass, sigma mi, that's actually just going to be m plus big M. Now, to move into this reference frame, I just need to subtract this velocity. I need to subtract this velocity from the velocities in my system already. So if I just move into my reference frame VCOM, I'm going to have the little mass moving with V minus mv over little m plus big M, and then big M moving with mv m plus m. I'm not going to put a minus sign here because my arrow is drawing left. I've drawn my arrow left. So if I then simplify this expression here, that's going to be m plus m v m over m plus m minus mv. So I'm going to end up with big mv over m plus m. And I don't need to simplify the larger mass. So then, once I have a look at my before and after, so this is going to be before, moving at big M V over little m v, and then my mass on the spring. It's a terrible spring, but sort of does the job. Little m v m plus m. That's my before. My after, I'll have that dot as the center of mass, and after the little mass and the little mass, let's scribble out, and the big mass will be at the maximum compression moving with 0 speed, but of course at the maximum compression. And the maximum compression can be just characterized as x. And so, all we have to do is now conserve energy in this frame. So before, they have kinetic energies half m big mv over m plus m squared, plus half big M little mv over little m plus big M squared, and that equals half kx squared. All I have to do is get rid of the halves, and then factorize as much as I can. So I can factorize out m plus m all squared. We'll do it step by step. I can also do a v, take out v squared immediately. So I'm left with m squared plus m squared equals kx squared. I can take out little m times big M, so this will be mv squared over m plus little m squared times big M plus little m equals kx squared. Cancel these out and then divide through by k. Squared over k m plus m is equal x squared, and I just have to take my square root. So x will therefore be v, because v is squared, square root m over k m plus m. And there we are.